Now let's learn theorem 10.1, and this theorem says when you connect the center of the circle to the point of contact, that means the point where the tangent touches the circle, then that line is going to be perpendicular to the tangent. So that's how we saw it through the figure. So this is the circle, then we draw a tangent to it, then we draw a line that connects the center of the circle to the tangent at point of contact. So this line is going to be perpendicular to the tangent. In other words, tangent is also going to be perpendicular to this line. And now we want to show or prove that this line is perpendicular to the tangent, and we are going to use negation method. That means we will first we will assume that this line is not perpendicular to the tangent, some other line is, and then as we go on we will see that the case is that the other line which we have assumed is perpendicular to the tangent is not actually possible. That's why this line is going to be perpendicular. Let's see how we do it. But before that, I want to make something clear so that when we try to prove by negation, it's clear to you that how I got to the conclusion that it is indeed perpendicular to the tangent. The radius is perpendicular to the tangent. So I want to connect a line. I haven't pointed out the center over here, but here I'm drawing a line from the center of the circle to the tangent, so it connects the tangent in the center of the circle. And now if you look at it, there are two parts to this line. The first one from the center to the radius, this one, and then the other part from the boundary of the circle to the tangent. So this line is going to be the radius plus the distance between the boundary, from the boundary to the tangent. Now you have to remember this blinking line when we solve this problem, or when we prove that the line that connects the center of the circle to the tangent to the tangent at the point of contact is going to be a perpendicular. So this is the center of the circle, and this is the line that connects the center of the circle to the point of contact, and this line is going to be perpendicular. So we want to assume that this line is not perpendicular. Now I try drawing other lines. This one, actually to prove it I just need to draw one line, but I'm just trying to show you so that it's clear that I mean even it is visibly clear that this is not the case. So I draw lines on both sides of the line, the dark black line that connects the center and the point of contact. That is this, like this, OP1 dash, P2 dash. I draw one more on both the sides, like this. This is P3. I just need only one line to prove it, but I'll do it anyway. So OP is the radius here, and now I want to move towards OP1 dash, or OP. You can do any one. So OP is always going to be less than OP1. Why? Because OP lies just on the tangent, where the tangent is touching the circle. So it means it is at the boundary of the circle. That means it is the radius. And OP1, the P1 point is on the tangent, but the tangent touches the circle at only one point, that is at the point of contact. So P1 is going to lie somewhere outside the circle, because there is only one point P that can be on the circle and the tangent both. But P1, since tangent touches a circle at only one point, it is going to be somewhere outside the circle. So P1 is going to be greater than that. And if you remember that blinking blue line, that was the extra part, the distance between the center, the boundary of the circle to the tangent. So here it is not visible; it is too close to the tangent and the the circle where they are touching. But you will see it in P2. The distance between the distance of between point P2 and the center O is the radius plus the distance between the boundary and the P2. So we can conclude the same thing about all other lines that we drew connecting the center of the circle to the tangent. They are going to be less than OP, like this. This is OP, this is going less than OP3, also OP, less than OP3. So what's the conclusion? Well, you know that when I draw a line from a point that connects a point on the other line, it is perpendicular when the distance is shortest, or perpendicular is the shortest distance between a point and the line. In this case, you see that among all the lines, be it OP1 dash, OP2 dash, OP1, OP2, anything, the shortest distance between the center, between the point O and the line is OP. That means by this fact I should conclude that OP is the least distance between O and the line that is tangent here. So if it's the shortest distance between that point and any other point on the line, then this line should be perpendicular, right? So we have proved it that the OP is perpendicular to the tangent. So this is because this is the shortest distance. And why is this the shortest one? Because no other point on the tangent lies inside the circle or on the circle. They are just outside the circle. So any line that is going to connect the tangent at any point has to go outside the circle except the point of contact. That's why it is the shortest line, and the shortest line is perpendicular. So we have proved it here.